Okay, so what did we do in our electrochemistry, the last topic which we did? That was we did the Faraday's laws and then we did the applications of electrolysis, right? Now today we are going to talk of conductors. Conductors and conductance and conductors. We already know what conductors are. Conductors are anything which have the capability to conduct electricity. That is what conductors are, right? Now to explain a little detail of conductors, there was a theory which was proposed by Arrhenius, and the name of the theory that was known as Arrhenius theory of electrolytic dissociation. Arrhenius theory of electrolytic dissociation. We had already studied that an electrolyte that conducts electricity by movement of ions. This theory tells us how the movement of ions or how these electrolytes they are dissociated and what are the factors which are going to affect the dissociation and hence the conduction. Okay, so let's go on to the postulates of this theory. The first postulate of this theory is that whenever an electrolyte is dissolved in water, it dissociates into its respective ions. Okay, so whenever we are putting any electrolyte into water, it dissociates into its respective ions. These ions, they are of two types. The first type of ion, that is positively charged, and the positively charged ions, they are known as cations, right? And the second is negatively charged, and the ions, they are known as anions. As for example, we are taking an electrolyte AB and dissociates into A positive plus B negative. So A positive over here, this is going to be the cation, and B negative, that is the anion. An example which we can take over here is that of NaCl. When we dissolve NaCl in water, NaCl immediately dissociates into its respective ions. Okay. Then number 2, the process of splitting up of ions. The process of splitting up of ions, this process that is known as dissociation. This process is known as dissociation, and the degree of dissociation is represented by alpha. Degree of dissociation is the amount of total electrolyte which has dissociated, right? So alpha, that is given as what? Fraction. Fraction means the amount, number of molecules or the fraction of molecules dissociated upon total number of molecules. Upon total number of molecules. So alpha, that is equal to number of molecules dissociated upon total number of molecules, and this alpha, that is known as what? It is known as degree of dissociation. Okay? Then the third postulate is that the electrolytes which completely dissociate, the electrolytes which completely dissociate, they are known as strong electrolytes, and degree of dissociation for these electrolytes, that is always equal to 1. Then number 4, the electrolytes which do not completely dissociate, they are known as weak electrolytes, and alpha, that is degree of dissociation for such electrolytes, that is always less than 1. Right? Now when we are talking of any reaction, the dissociation reaction, this is what we are getting, A positive and B negative, right? And at equilibrium, we say that the equilibrium constant K, that is equal to concentration of products upon concentration of the reactants, right? Where K is the equilibrium constant. Now the value of K, that tells us about the ionization constant, or about the degree of dissociation. So we say that K has a larger value. K is going to have a larger value for strong electrolytes, right? And K is going to have smaller value for weak electrolytes. Okay, so K is going to have a larger value for strong electrolytes and K will have a lower value for weak electrolytes. Then number 6. Number 6, when we say that whenever an electric current is passed through an electrolyte, the cations which are positively charged, they move towards the cathode in an electrolytic cell, right? This we have already done. And anions move towards the anode. We also know that at cathode, reduction takes place, and at anode, always oxidation that is going to take place. ठीक है? फिर उसके बाद conductivity of electrolytic solution depends upon conductivity of electrolytic solutions. Conductivity, that is going to depend upon what? It will depend upon the nature of the solute, number of ions and mobility of the ions. So these are the three things on which conductivity that is going to depend. It will depend upon the nature of the solute, it will depend upon number of ions, and it will depend upon mobility of ions. ठीक है? फिर उसके बाद the last is the property of the electrolyte. The properties of the electrolytes that is equal to the properties of ions. For example, when we are talking of any acidic electrolyte, right? Like we are talking of HCl. So the electrolyte that is acidic, why? Because its ions is yielding H positive or producing H positive ions in solution. Therefore, the electrolyte that is acidic. In a similar manner, if you are doing KOH, it is basic because it is producing OH negative ions in solution. Okay, so the properties of the electrolytes, that is what? That is going to be properties of the ions which are given out in solution. So this was the Arrhenius theory. Then depending upon this, the factors on which the electrolytic dissociation or electrolytic conduction depends was formulated. Okay. So then next is factors affecting degree of ionization, right? Now when we are talking of degree of ionization, the first factor, that is nature of solute. It is said that whenever we have studied in class 11, that every ionic bond has some covalent character and every covalent bond that is going to have some ionic character. Okay, so nature of the solute means, when we are talking over here, if covalent bond predominates, if the covalent bond character is more, the electrolyte is a weak electrolyte, and for such electrolytes we have just studied that the degree of ionization, that is less than 1. Right? So if a covalent bond predominates, then it is a weak electrolyte and the degree of dissociation is less than 1. Examples which we can take over here is that of HCl and acetic acid and CH3COONA, sodium acetate. In all these, we can say the covalent bond that predominates, therefore the degree of dissociation, that is going to be less than 1, and the electrolytes, they are known as weak electrolytes. Another example which we can take over here is that of H2S, hydrogen sulfide. Okay? If the ionic bond predominates, right? If the ionic bond predominates, in that case the electrolyte is a strong electrolyte, and alpha for such cases, that is going to be equal to 1. Examples which we can take over here is that of HCl, NaCl, H2SO4. So all these, they are examples of strong electrolytes. Okay, then the second factor is nature of solvent. Okay, now when we are talking of a solvent, basically what does a solvent do? A solvent tries to break the forces of attraction between the ions of an electrolyte. For example, if you're taking, we put NaCl in water, so basic idea or basic application of the solvent is to break the forces of attraction, the bond between Na positive or Na and Cl, so as to yield two types of ions, which is Na positive and Cl negative. Okay, so it is said that this capability of breaking the ions by a solvent, that depends upon the dielectric constant of the solvent. It depends upon the dielectric constant of a solvent. Greater the value of dielectric constant, better will be the solvent. Or we can say more, it will have more capability to break the ions. Right? So when we are comparing the dielectric constant of water, the dielectric constant of water, that is 81. Right? It has the highest dielectric constant. That is the reason why it is also known as a universal solvent. Okay? And that of, let's say, ethyl alcohol, the dielectric constant is only 35. So it is not a very good solvent. Clear? So solvents, the dielectric constant, greater the value of dielectric constant, more is going to be the capability of breaking the ions into their, breaking the electrolyte into their respective ions. Then third factor is dilution. We say that conductance is inversely proportional to concentration of the solution. If the solution is more concentrated, then the ions, they cannot be dissociated effectively because they are bound with greater forces of attraction. Therefore, conductance, that is going to be less. On diluting this solution, it is seen that more ions they are produced and hence the conductance increases. So therefore, dilute solutions have more dissociation. Dilute solutions have more dissociation. Okay, so the degree of ionization, that is going to increase with increase in dilution. Then the last is temperature. As the temperature increases, we know that the kinetic energy of the molecules will also increase. Right? If the kinetic energy that is going to increase, then in that case what will happen? The forces of attraction will break. The speeds of the molecules will increase and hence the degree of dissociation will also increase. More the degree of dissociation, more is going to be the conductance. So temperature is also directly proportional to alpha, or you can write down directly proportional to degree of dissociation. Is directly proportional to degree of dissociation. Okay? Is it clear? So these are the factors. Then next we are going to today discuss the first type of conduction, which is known as electrolytic conductance. Electrolytic conductance. We have done this term many times. What do we mean by electrolytic conductance? Electrolytic conductance, it is the conductance due to ionic conductors. That is what electrolytic conductance is, right? But when we are talking of metallic conductance also, electrolytic conductance may you can say the movement of ions that brings about the conduction in electricity. Whereas in metallic conductors, the movement of electrons, it is going to bring about the conduction in electricity. Now, whether we are talking of the conductors, whether they are metallic or they are electrolytic, in both the cases, they obey the Ohm's laws. Right? Now, according to Ohm's laws, it is said that the voltage applied through the cell, that is directly proportional to I. Okay? Or we can say that V, that is equal to IR, where R, that is resistance to the flow of current. It is resistance to the flow of current, right? Now this resistance, the unit when we are talking of resistance, the unit of resistance, that is ohms, right? And it is said that resistance is directly proportional to the length of the wire and area of cross section of the cell, right? Clear? So when we are talking of this, we can say that R, that is equal to rho L upon A. Rho over here, it is specific resistance. Rho is the specific resistance and it can be, when you can say, it can be defined as we are saying that the length of the wire that is equal to 1 centimeter and area of cross section that is equal to 1 centimeter square. 1 centimeter square, then in that case your resistance becomes equal to specific resistance. So we can say that specific resistance is the resistance when the length of the wire is 1 centimeter and area of cross section of the wire is 1 centimeter square. Then that is known as specific resistance. When we are talking of the units of specific resistance, the units of specific resistance is going to be what? Rho ohm centimeter. Right? Now this specific resistance, it is inversely proportional to specific conductance. Right? So we are saying that the reciprocal of specific resistance that is denoted by kappa. Okay, so this kappa, we can say that kappa that is equal to 1 upon rho. This kappa that is known as specific conductance. Okay, so kappa over here that is known as what? It is known as specific conductance. Now let's see what is the relationship between resistance and kappa. Relation between resistance and kappa. We know over here that resistance that is equal to rho into L upon A, right? And rho that is equal to 1 upon kappa into L upon A. Okay, so let's take kappa on the other side. R into kappa that is equal to L upon A. In a cell, the length of the wire and area of cross section that is always constant. Therefore, we take this term L upon A as a cell constant, which is denoted by G star. Okay, which is denoted by G star, such that we have R into kappa that is equal to G star, where G star that is the cell constant. When we are looking at units of kappa can be derived from here. It will become per ohm, right, per centimeter. Per ohm per centimeter, and this per ohm that is also denoted by S, which means Siemens. So the unit of kappa that is going to be Siemens per centimeter. Okay. Now then when we are talking of specific conductance, we have spoken of specific conductivity. Then how will you define the specific conductance? When we are defining, like we have defined specific resistance as what? It is the resistance when 1 centimeter length of the wire is taken and the area of cross section of wire is 1. Similarly, specific conductance becomes equal to conductance when the length of the wire is 1 centimeter and area of cross section that is equal to 1. Today we are going to discuss two types of conductances over here. The first one that is known as equivalent conductance. Okay, so we have the first kind of conductance, which is known as equivalent conductance. Now, what is equivalent conductance? You can write down. It is defined as the conductance of all the ions produced defined as the conductance of all the ions produced by 1 gram equivalent produced by 1 gram equivalent of an electrolyte in a given solution. Right? So we denote it by lambda E. This is what equivalent conductance is. Now to understand equivalent conductance, what do we do is we formulate a cell which is in the shape of a cube. Right? So we are taking a cube. Okay. Now in this cube, rectangular trough, or you can say we've taken a rectangular trough, and in this we are taking two metallic electrodes, this and this. Both of these, they are metallic electrodes. Okay. And you can say the distance between the two metallic electrodes, that is exactly 1 centimeter. Right? So the metallic electrodes, they are 1 centimeter apart. Okay, so the length, that is going to be 1 centimeter, and the area of cross section, it is 1 centimeter square. Clear? Now in this particular conductor, what we do is we take one electrolyte which has a volume of 1 centimeter cube, or we can say that it has a volume of 1 milliliter. Right? Then after that, we also take an electrolyte which has 1 gram equivalent normality. Right? 1 gram equivalent normality, that is the electrolyte which we have taken. Now when we are talking of conductance, the conductance in this case, because everything we are taking over here as 1, it can be said that it is equal to what? It is equal to specific conductance. Okay? It is equal to specific conductance, but also when we are taking 1 gram equivalent, so we say that this is also equal to equivalent conductance. Okay? So what have we done? We've taken this trough with two metal which are 1 centimeter apart from each other, and in that we have taken 1 milliliter of an electrolyte with a normality with a equivalent weight of 1 gram equivalent. Okay? Now when we are talking of conductance, because everything over here, the length is 1, the area is 1, therefore conductance, that becomes equal to specific conductance, and because we have taken 1 gram equivalent, so we can also say that the conductance is equal to equivalent conductance. Now what we are going to do over here is, we are going to dilute the solution in this and increase the volume from 1 milliliter to 9 milliliters. Okay, so hypothetically we say that when we have diluted the solution to 9 milliliters, hypothetically we say that we have divided this rectangular trough into 9 different cubes. Okay, each cube that is now going to contain 1 milliliter. First, the entire trough was carrying 1 milliliter. Now we have diluted it to 9 milliliters, and hypothetically we are saying that we have divided the trough into 9 cubes, and each cube is containing 1 milliliter of solution. Okay, now in such a case, the equivalent conductance remains same. There is no difference in equivalent conductance. But when we are talking of specific conductance, it becomes 1/9 of the original value. Okay, so we are saying that 1/9, why? 1 centimeter cube on unity. It is a unit factor. As there are 9 cubes, every cube in the 9 cubes will have a different specific conductance. So specific conductance, because of 9 cubes which are formulated, the specific conductance that reduces to 1/9. Clear? Now when we are talking of equivalent conductance over here, it means that the equivalent conductance lambda E, that becomes into 9 into kappa, 9 times the specific conductance. Clear? 9 into kappa. Now we know that the equivalent conductance in general, if we are talking, we have increased the volume to 9. So in general, if we are talking, lambda E, that will become equal to kappa into volume. Whatever is the volume, because 9 ml is the volume which we are taking over here, right? And volume can be written as what? Thousand upon concentration. Okay? So volume, that can be written as 1000 upon concentration. Because over here we are taking the equivalent conductance, therefore lambda E becomes kappa into 1000 upon normality. Clear? So equivalent conductance, that is equal to kappa into 1000 upon normality with a unit of Siemens centimeter square per gram equivalent. Siemens centimeter square per gram equivalent. Okay, that is what is lambda E. Have you understood the difference between specific conductance and equivalent conductance? Okay, so in a similar manner, when we are taking into consideration the, instead of gram equivalence, we are taking number of moles, right? Instead of gram equivalence, we are taking number of moles. In that case, that is known as molar conductance. And molar conductance, that is denoted by lambda M, that is equal to kappa into 1000 upon molarity. Okay, molarity. Kappa into 1000 upon molarity. Is it clear? When we are talking of units, then the units over here become Siemens centimeter square per mole. Okay, and we say that equivalent conductance, that is equal to molar conductance upon N. This is a relationship between equivalent conductance and molar conductance. Equivalent conductance, that is equal to molar conductance upon N, where N, that is equal to molecular mass upon equivalent mass. Right? So this is, we are going to till here only today. We have to do numericals regarding this, but before that we will go on to Colruyt law, and after that we will do all the numericals together. Okay?